Chemistry and Society, Synthetic Cannabinoids by Jack Hogan. My topic is about synthetic cannabinoids and specifically about their prominence in Britain from around 2009 to 2016. In Britain, cannabis is illegal, but it's still sold illegally for relatively high prices, and there's still a lot of people consuming it. So, synthetic cannabinoids were designed to be legal versions that mimic the effects of cannabis so they could be sold not just legally but cheaper to the people who all consume cannabis. And they could do this because cannabis was only illegal because its active chemical THC was banned. But if you slightly altered the molecular formula for THC, it technically wouldn't be illegal because it wasn't the exact formula that was banned. So that's what chemists did, and they slightly altered the molecular formula and they sold it under incenses or other products that were labeled not for human consumption so they could have like a legal guise for what they were selling, but it was really just supposed to be a recreational drug. However, the British government caught on to what these companies were doing, and they would just ban the new slightly altered version of THC that they make. But then the company would just make a different alteration, and then that would get banned as well. And then over time, their alterations would get more and more drastic until eventually the molecule would barely even resemble THC, and the effects are super unpredictable. And even at one point, it was 100 times more potent as cannabis, which is what it was supposed to replicate. So over time, it became even deadly, and many overdoses, and the withdrawals were extremely bad, extremely addictive. Some people describe it as even worse than heroin when it was supposed to mimic a way less potent recreational drug. And what makes them so dangerous is that because there's so many of these different alterations, these companies, you could have the same brand of spice. Like if you look at this picture here, this is a packet and it's a brand called Insane Joker. So if you were to get a packet of this at a certain time, it could be a completely different drug than something a couple months later. Or even in the same batch, sometimes there's very huge alterations. And since it's not technically for human consumption, there's no testing. You have no idea what the effects are, and they don't really care because as long as there's some kind of high to it and it gets people addicted, that's all they're looking for. And that's what makes these drugs so dangerous, just how unpredictable they are. Again, if you look at the little label right here, it says herbal incense blend, which is how they got away with it. So the societal impact of synthetic cannabinoids. So even to this day, they've been completely outlawed since 2016, but it's still prominent in Britain because within that time period of more than half a decade, so many people got addicted to it that now, even though it's illegal and way more expensive than it used to be, people are still willing to go out their way for it. And I got a little collage of people who are on it, and you can see at this point, it just completely knocks you out. Like the effects aren't even similar to cannabis anymore. It's abundant throughout prison. Over 95% of the homeless population use it regularly. It's ideal to pass drug tests because you can get tested for marijuana, but you can't really get tested for these drugs because there's so many possible drugs it could be because it's not a single compound. So you can't, even if you're caught with it, yeah, they don't really know what it is. Um, Within the period, I mean, it still probably is cheaper than cannabis, but especially from 2009, 2016, since it was legal, it was like half the price of cannabis. Um, it's extremely unpredictable. The withdrawals are heroin-esque. At this point, it makes most users unconscious. Um, the at the time, the companies who were selling it were profiting, obviously. And now just people who sell it illegally are profiting. Um, and drug workers describe it as the zombie drug, which I mean, you can tell by this kid over here. And that their effects they experienced with the people they work with were far worse than heroin. And again, like I said, with the possibility being 100 more times potent than the original THC compound. So we'll do a quick overview of my lesson. We're going to start with the first unit, organic chemistry. We're going to go over naming alkanes, alkenes, and alkynes, as well as a couple of reactions. For Unit 2, atomic structure, we're going to go over quantum numbers as well as intermolecular forces. For thermochemistry, we'll be doing some enthalpy calculations with bond energies. And for the fourth unit, equilibrium, we're going to go over an equilibrium law example. So mine's on organic chemistry. Right off the bat, what are the differences between the two molecules? So these are the IUPAC preferred names. You can just ignore those. But and in this case, for these lines here, you can assume there's carbons on the end of each of these. So if we were to compare these two molecules, this one obviously has a longer carbon chain. They both have carbonyl groups, which is these double bonded oxygens to a carbon. They both have chlorides attached to a carbon. And so you wouldn't think they're that different from each other, but the one on the right can actually be used to purify water, when the molecule on the left is got the common name phosgene and is considered a chemical weapon. Let's start with naming alkanes. So you got to find the parent chain first. So to find the parent chain, which is the longest amount of carbons possible, in this example it would just be 2. So you use this chart over here. So the amount of carbons correspond with the name. So 1 carbon is methane, 2 carbons ethane, 3 carbons is propane, and 4 carbons is butane. The rest kind of just correspond with shapes. You can think 5 pentagon, pentane, all the way to 10 decagon, decane. So in a case where you got branches like these, so when you number them, you don't know the branches yet. You got to find a way you can number as many carbons as possible. So if you were to number it from here to here, or here to here, or here to here, it wouldn't be as much. So, and you also got to keep in mind which side you start numbering. So if you started here, this first branch would be on the 4th carbon, when this branch is on the 3rd carbon, and you want these branches to be on the lowest carbon possible first. So 1, 2, 3, 1, 2, 3, 4, you start numbering here. And these branches are called substituent groups, and in this case they're alkyl groups. And you would just name them like alkanes, but you change the ending instead of ane to YL. So in this case it'll be a methyl group, and in this case it'll be an ethyl group. And when you name these groups, you gotta see which number carbon they're on. So this methyl is on the 3, this ethyl is on the 5 carbon, and then when putting it all together, you get the octane, because 1 to 8, that's 8 octane, and then you got the 2 groups with their numbers on them. But the ethyl has got to go before the methyl, because you name these groups alphabetically, not including their prefix if they have a prefix. And a prefix is if there's multiple methyls, for example, it'll be dimethyl or trimethyl, etc. So when we name alkenes and alkynes, it's fairly similar to alkanes. Alkenes just have at least one double bond. So it doesn't matter how long it is, how many carbons it's on. If there's a single double bond, it's no longer an alkane, it's an alkene. And the same thing for alkyne, but if there's a single triple bond. If there's a double and a triple, it's now an alkyne because it's got higher priority. I'll go over that in the next slide. So naming them is very similar to alkanes. 2 carbons, instead of ethane, it's ethene. 3 propene. However, it gets a little more complicated here, because you got to keep in mind this double bond could be on either one of these carbons. So when you name it, you also got to number which carbon it's on. And so the reason this is 2 and not 3 is because it doesn't matter which side you number it, it would be on the 2, because you got to go from the lowest possible. So in this case, you wouldn't have to number it, because if it's on the 1, it's like implied. But you could do 1 propene. Excuse me. Same thing for alkynes, and they both have the same rule for substituent groups as alkanes. So here's the priority list I mentioned. So you can see alkynes are a higher priority than alkenes and alkanes, which is why their naming is prioritized. So these ones are a little more complicated. So in this case, we got two double bonds. So you got to number both these bonds, um, and you got to add a prefix before the ending. So because there's two, it's diene, and the number one is separated by the three with a comma. So this carbon's on the one, this one's on the three. The It's a 1,3 butadiene. And the reason this A is added is because IUPAC likes French, so they add vowels here, so it's not just DT. And in this case, something similar happens, but the opposite with the naming. So we got a double bond and a triple bond. So it's an ene and an ine. It's still considered an alkyne, but you got to show where the double bond is and where the triple bond is. So the triple bond is on the one because it's a higher priority, so you got to number that one first. The double bond is on the three, and you can see this ene is missing an e because IUPAC French doesn't want an EY, two vowels beside each other, so they take off the E there. So our first connection of the first unit is if we were a chemist, and let's say this was our starting compound, we can now see how they can make these slight alterations. So this compound, we go 1, 2, 3, 4, 5, 6, 7, 8. It's an octane, and there's a methyl on the 3, so the name is 3-methyl-octane. I can slightly adjust it by, look, instead of putting the carbon on the 3, I put it on the 4. It's now 4-methyl-octane. But now the British government is like, you're not allowed to put any methyls on an octane. So I can, oh look, it's now an ethyl. But now this could have a very different effect than what these had. And you can see that here. So this is THC compound. And I remember when I first watched this documentary a couple months ago before I took this chemistry class, and I saw these pictures and I had no idea what's going on. Now I actually understand it a bit after organic chemistry. So you can see the little differences in like the methyl groups we just went over. You can see right here, the original THC, one of the earlier versions of synthetic cannabinoids, they just added some methyl groups here. There's some other slight changes like this OH group. And then eventually they got so, like, it doesn't even resemble THC. So you can visually see how over time the differences got more drastic. And for the second part of this unit, we're going to go over a couple reactions. So our first reaction, substitution halogenation. We start with a hydrocarbon, in this case methane, and we add a halogen under UV light or heat. We get an alkyl halide and an acid. And this reaction has a mechanism. So you can see the UV light or heat can break the bonds between these two bromines, or it could also happen between a carbon, one of these hydrogens over here, but for this example, we'll just assume it breaks the bromines, and it creates free radicals. So one of these free radicals will break a bond between one of these hydrogens connecting to the carbon, and it will attach in its place, creating the alkyl halide, and now the extra hydrogen will attach to the other free radical, creating the acid. Our second reaction, substitution hydration. We start with an alkyl halide and water, and we get the products alcohol and an acid. So you can see this, the oxygen and the hydrogen from water create a hydroxyl group that attaches, and this bromine, which is the halogen, breaks off and attaches to the extra hydrogen from the water. Our third reaction, dehydration of alkanes or oxidation. We start with an alkane, it oxidizes, and we get an alkene and water. And I explain this a different way by, instead of saying oxidation, we can visually add the oxygen so you can see what happens. And these two hydrogens connect to that oxygen, making a water. And now since these two hydrogens are missing, the carbon will double bond, so it has all 4 bonds. Our fourth reaction, addition with water hydration. We start with an alkene and water, and we get an alcohol. So you can see the hydroxyl group being formed from the water, and then the extra hydrogen attaching to the other carbon. so there's no more need for a double bond. So our second connection for the organic chemistry unit, we're going to take a look back at this THC and the second variation that we looked at before, and I mentioned the OH group that was added up here. So if you look closer at that, we're going to not worry about the rest of the molecules, or just have it as R for now. Um, if I was a chemist and I wanted to add this hydroxyl group from an alkane to an alcohol, how would I do it? So from the four reactions we just did, we can use the first two reactions. So we can start with a hydrocarbon, add a halogen, and we get an alkyl halide, and then an acid is a byproduct. But if we use that alkyl halide and add water using substitution hydration, we can get an alcohol and an acid byproduct, which is what we want from the reactant we want. But we can also use our third and fourth reaction. So we can start with the alkane. We can oxidize it, so it becomes an alkene plus water. And then we can use that alkene and water to make an alcohol with addition with water. I think these reactions are more efficient because for the fourth reaction, you're really just using the products of the third reaction, and you get that same product we were looking for, the alcohol. So now you starting the second unit. Mine's on atomic structure. Why do frozen pipes explode? So you may be thinking because water expands when it freezes, and that is the reason. But um, when I explain intermolecular forces, I'll be able to explain that further. But first, we're going to start with the quantum numbers. So the principal quantum number, or n, represents the size and energy of the atomic orbital. So you can find n by the row an element is in the periodic table. If it's the fourth row, the n value is 4. So it's equivalent to the period of the element. It represents the maximum amount of electrons in the orbital, yeah, as well as the size of the electron cloud and the energy of the electron at that level, and the probable distance from the nucleus. These aren't to scale. The distance between the first and the second is much greater than the second and the third. Now our second quantum number, which is the sublevel quantum number, or cursive L. L can be represented by a letter like S, P, D, F, and all possible L values are from 0 to whatever your N value is minus 1. And you can also find this L value by this periodic table here. So you can see here are all the S's, which would be 0. Here are all the D's, which would be 2. All the P's, which would be 1. So if your element was in the p orbital, it would have an L value of 1. If it was in the f, it would have an L value of 3. This value indicates the shape of the orbital, so like the s, which is a sphere, and the p orbital, which is the dumbbell. The third quantum number is the magnetic quantum number, or ML, and this describes the orientation. So you can see this s orbital, doesn't matter how you spin it, the orientation is going to stay the same. But the p and the d orbital, as well as the f, you can actually change the orientation, as you can see here, and that's what this quantum number determines. So you can find this by all the possible ML values. To begin with, is from the negative L value to the positive L value. So if your L value is 1, you would have negative 1 to 1 if you were in the p suborbital. So for this example, we're going to be using fluorine. That I put the little star here so you can see it. So because it's in the p orbital, our L value is 1. So we're going to go minus 1, 0, and 1. And now we're going to fill in our electrons. So there's 1, 2, 3, 4, 5 electrons in this 2p orbital. So when we fill them up with the arrows, we go 1, 2, 3, 4, 5, and we number that way due to Hund's rule. So when the orbitals are equal energy available, the electrons are assigned to 1 each first from left to right, like that. And then our L value, our ML value equals 0 because that is the last arrow we landed on. Our last quantum number is the spin quantum number, ms. So this quantum number describes the direction of an electron spin. So it can either spin clockwise or counterclockwise. Clockwise if it's positive a half, or counterclockwise if it's negative a half. So we can use this chart here where each of these suborbitals are separated into two halves. The left half being positive a half, or clockwise, and the right half being negative a half or counterclockwise, and that works for P as well as D, S, or F, both separated into halves. And we can also solve it similarly like we did with the previous quantum numbers. So we're going to use the example of fluorine as well. It's got 5 electrons in the p orbitals, so it goes from -1 to 1, and when you fill in our 5 electrons, now our last electron is facing downward, which represents negative a half, or counterclockwise. And also go over the Pauli exclusion principle, which is in any given atom, no two electrons can have the same set of 4 quantum numbers. Our first unit 2 connection. So we're going to look at the THC molecule again, and it only contains 3 elements: hydrogen, carbon, and oxygen. So we're going to find the quantum numbers for those 3 elements. So hydrogen is the easiest. It's in the first row, so n equals 1. The L value can only be 0 because n minus 1 is 0. The ml value also 0 because -0 to +0 is just 0. And then with our only electron, it is positive a half because it's facing upward. Carbon now is in the second row, so the n is 2. It is in the p section, so the L value is just 1. There's this chart here. The ml value is 0 because when we fill in our electrons from -1 all the way to +1, it lands on the 0. And the ms value is positive a half because it's facing upward. Last, oxygen is also in the second row, so the n value is 2. The L value is also 1 because it's in the p section. The ml value is -1 because when we fill in our electrons, it's in the -1 orbital, and then the ms value is negative a half because it is facing downward. And now onto the weak intermolecular forces, starting with dipole-dipole forces, which is the attraction between the partial positive and the partial negative charges of a molecule, which is these symbols here, the partial positive, partial negative. And the strength of the force is determined by a molecule's polarity and is only present in polar molecules. And it is more significant, the force, and the greater the amounts. So you can see here, this molecule right here, the partial negative, is attracted to the partial positive of another molecule. So our second weak intermolecular force is hydrogen bonding, which is a stronger dipole-dipole force, and it occurs when a hydrogen atom is bonded to an oxygen, a nitrogen, or a fluorine, and is attracted to the partial negative charge of another atom. It is the strongest of the weak intermolecular forces, and like we talked about earlier, about the pipe exploding due to the expansion of water, it is due to this intermolecular force, hydrogen bonding. And you can see in this picture here, similar to dipole-dipoles, the partial positive and the partial negative, it's just stronger with these specific elements. And our last weak intermolecular force, which is the weakest, is London dispersion. It's the attraction between nonpolar molecules, and it's a temporary dipole-dipole force when there is an uneven balance of electrons. And it's present in every single molecule, and it is by far the weakest intermolecular force. For our second unit 2 connection, we're going to be looking at the melting points of these 3 molecules, starting with THC and the 2 later variations I showed you earlier. So the higher the melting or the higher the boiling point of a molecule corresponds with the strength of the intermolecular forces, because it's harder to break the bonds between the molecules. So in this chart over here, we can see that the carboxylic acids have the highest melting point because they got both the polar hydroxyl group as well as the carbonyl. The alcohols are behind it with, since it just has a hydroxyl group, but still pretty high. The ethers aren't close to as high, and neither is the alkanes. And also the length of the carbons in general, they're just the greater the mass, the more intermolecular forces due to the amount of London dispersion. So when you look at THC, it's got a or look at the melting points instead of the boiling points, are these three, because these two molecules are very niche and I couldn't find their boiling points. But if you look at the melting point for THC, it's got a hydroxyl group. So just from looking at this molecule, even before looking at this melting point here, you can probably determine it's got a higher melting point because it's got another hydroxyl group, while this one has no hydroxyl groups. So according to our chart here, it should be lower than both of these two. And yes, it is. It does have a lower melting point than these two molecules. And continuing with our third unit, thermochemistry, we'll start with enthalpy. The enthalpy of a reaction is the net energy difference between the making of product bonds and the breaking of reactant bonds. And the units for enthalpy, or delta H, is either joules or kilojoules. So if the enthalpy of a reaction is positive, the reaction is endothermic. And if the enthalpy is negative, the reaction is exothermic. And you can see why in these graphs here. So for an exothermic reaction, for both of these reactions, the y-axis has the potential energy in kilojoules, and the x-axis has the reaction pathway. So for the first reaction, endothermic, the reactants have a certain amount of potential energy, and the products also have a certain amount of energy. And you can see that difference here between the energy of the reactants and the products is the enthalpy. And this difference will be positive, which is why endothermic reactions have a positive value. This chart also shows the activation energy required for the reaction and the activated complex. The exothermic reaction, the opposite occurs. So we start with the reactants at a certain amount of energy, and the products have less energy. And since this difference goes lower, it will be a negative difference, which is why exothermic reactions have a negative delta H value. We can calculate enthalpy using bond energies, because the enthalpy of a reaction is directly proportional to bond energies. Bond energies are the amount of energy required to break 1 mole of bonds between two atoms. So these average bond energies are in kilojoules per mole, and they're predetermined. They'll be given when you solve these questions. So the general formula just looks like the sum of energies required to break old bonds, which is positive, plus the sum of energies released to form new bonds, which are negative. Or you can just use this formula here, which is the sum of reactant bonds broken minus the sum of product bonds formed. So we can apply this to one of our reactions we used in the first unit for the THC molecule, our first reaction. So because these R values, we want to have all the bonds available to calculate the bond energies. I'm just going to assume there's only one more carbon here for the R value and make this an ethane. So when we look back at our charts, we can find the specific kilojoules per mole of the average bond energies between each of these bonds. So the two carbon, the bond between the two carbon atoms, we look back at our chart, carbon carbon, that's how we got that number, and we solve that for all the types of bonds. But we also have to take into account how many of these bonds there are. So when we do our equation here for our carbon bond, we only have the amount here multiplied by 1 mole, but for the carbon hydrogen bond, we have it multiplied by 6 moles because there's 6 of these bonds. And then we follow this formula here. So we calculate all these minus all of the products. And the reason I crossed out all these moles is so you can see how we got rid of the mole units and we're just left with the kilojoule units. And then we get just these values in kilojoules, and you get the final answer, the delta H being negative 33 kilojoules. And because the delta H is negative, it will be an exothermic reaction. And on to our fourth unit, equilibrium. Chemical equilibrium occurs in a system when the forward and the reverse reactions are occurring at the same rate. The forward meaning reactants to products, and the reverse meaning products to reactants. The concentration of both the products and reactants is constant at equilibrium. Equilibrium can only be obtained in a closed system, and the concentrations of the reactants to the products don't need to be the same, they just need to be constant. So in our first graph here, we have rate and time. So the forward rate of reaction and the reverse rate of reaction, they equal at about here. So equilibrium is reached at about here because they're both at the same rate. For the second graph, amount and time, you got the amount of reactants and the amount of products, and you can see equilibrium is reached at about here because even though the amounts of both are different, they're both constant. Equilibrium law. Since at equilibrium, the forward rate is equal to the reverse rate of the reaction, the rate law of the forward reaction would be equal to the rate law of the reverse reaction, which you can see here. The rate of the forward reaction, the concentrations to their coefficients, and equals the rate of the reverse reaction. And we get this little formula here. KEQ equals the concentration of the products over the concentration of reactants. The concentrations need to be at equilibrium, and K represents the ratio between the forward and the reverse reactants, and KEQ represents equilibrium constant and doesn't have any units. So if K is equal to 1, the concentration of the products is equal to the concentration of the reactants at equilibrium. If K is greater than 1, the products are favored at equilibrium, and if K is less than 1, the creation of reactants is favored at equilibrium. And when calculating KEQ, only use the concentration of gases and aqueous solutions, because solids and liquids don't change concentration with their amount because their density is constant. So onto our unit 4 connection. We're going to use the same reaction we got at the beginning for our THC, but we're going to replace the R, which is the single carbon, so we can use everything available in this question. We need to calculate the concentration of HBr at equilibrium if 3 mole of ethane and 2 mole of Br2 was placed in a 2-liter container at 35 degrees Celsius. And we're also given our KEQ value. So our first step is we got to find the concentrations, and we're given a mole value and we're given a volume. So we can solve for molar, which is equivalent to concentration. So molar equals moles over volume in liters. So we can solve for the concentration of ethane by doing 3 moles over 2 liters, and we get 1.5 molar. And the same for Br2. We can do 2 mole over 2 liters, and we get 1 mole. So then we can make an ICE table. And ICE stands for our initial concentrations, our changing concentrations, and our concentrations at equilibrium. And right off the bat, you can see we have a liquid here, and our rule here, we don't use solids and liquids because of their density. So we're going to cross this out of our ICE table, and we're not going to worry about that for our calculations. So we're going to sub in our initial concentrations, which we just solved. So we got 1.5 molar here and 1 molar here. And we're going to assume there's 0 products initially. We're going to subtract a variable from both our reactants and add a variable to our products because in a reaction we're going to be losing our reactants and gaining a product. And then we can signify our concentrations at equilibrium by doing our initial minus our change. So you got 1.5 minus x will be our concentration at equilibrium. 1 minus x will be this concentration at equilibrium, and HBr at equilibrium will be equivalent to x. So we need to solve for x to figure out these concentrations at equilibrium. So we can use our equilibrium law equation, and we can sub in our given KEQ, and right here we can sub in our products over reactants, so our x variable over our 2 reactants. And now usually if the hundreds rule didn't apply, we might have to do some crazy solving for x, but because the hundreds rule does apply, which is if the reactants divided by 100 are greater than our given KEQ, so if this 1.5 divided by 100 is greater than this number, we can remove the variables in the denominator. So that does apply. We don't have to use the quadratic formula, and we can get rid of these variables in the denominator. So now we have a much simpler equation, and now we can just solve for this single x, and we end up getting a value for x. And since our concentration at equilibrium for HBr is just x, and that will be our concentration of HBr at equilibrium, and this is in units molar. Thank you if you made it this far. These are my citations, and I highly suggest watching this. It's a short documentary. It's only like 10 minutes by Vice, but it kind of inspired this whole topic. But yeah, thank you for listening.